So thermistors are interesting, sort of very specialized kind of temperature sensor. You see them used in some places. If you recall from Richard's earlier slide on market share, thermistors was a small piece. Thermistors do get used. One of their values is they're very repeatable. Yellow Springs instrument, YSI, developed a lot of these curves as thermistors. They're sintered metal alloy, so they're a material that behaves consistently in response to temperature. There are two types of them. There are the PTC, positive resistance change with temperature, and that's similar to like what an RTD is the temperature gets hotter, the resistance goes up. But one that gets used a lot is the negative change, and so that's actually the resistance goes down as the temperature goes up. There's some applications for that. In fact, on another part of our business, not in temperature, but in RF power sensors, we make an RF power sensor that uses an NTC thermistor, and it operates at one very specific, we actually tune it to a certain resistance, but it's operating at about 150, 160 C. But they in general, they follow the Steinhart-Hart equation, which is basically a nonlinear, it's a logarithmic curve. And it's actually rather bendy. And so to really use them, you need to know, well, first that you can use them with the curve if you don't need real tight accuracies. If you need tight accuracies, you get the same thing. You get them patterned, you get them matched, and then you know what they'll be at a certain temperature. One of the real values is that they exhibit a very large resistive change. Let's go to this slide. So they exhibit a very large resistive change over their operating range. So you can see this one. This is a 10K. So at specified at basically room temperature 25 C. This is a 10K thermistor. And you can see when you get down to zero, you've almost doubled the resistance of it. So it's a very large change. And as you go out, it starts to get, it's harder to see the change out here as much. So it becomes less accurate. And then the materials start to break down when you get up to those temperatures as well. So, but if you want to use them at specific points, you do the same thing. You send them out to a lab. They stick them in a bath. They measure them, they tell you at this temperature you're going to see this resistance. And you can, with some thermistor instruments, you can put those coefficients into the instrument, and then you can get that easier. One of the real values of them is that they can be made very small. So in our RF power sensor, ours is about 8/1000ths of an inch. It's a very small bead, very sensitive. And so you get fairly fast response. Ours respond in a few milliseconds, which is useful. And another benefit that a thermistor has is it's actually quite interchangeable, so it will repeat. So again, back to that accuracy versus precision, if you can measure it and say at 75 C it produces this resistance, you'll be able to get something like 1/10 of a degree repeatability on that, and that's useful in certain applications. Fairly durable too. We have some sensors that have been out 20, 30 years, and the thermistor still behaves the way it did 20 years ago, which is really useful. And calibration, again, it's a resistive-based device, so it's similar to what you do with an RTD. You're putting in a dry well in a bath, and you're measuring the resistance, and you're coming up with a calibration for it.